Okay, in this video segment, we're going to cover the first part of Chapter 20, which deals with the statistical technique referred to as logistic regression. So just keep in mind that I'm going to post this, I'm recording this on Thursday, and we'll put this in Moodle. But if you haven't, I'm assuming you haven't taken your third exam yet, certainly don't worry about this. None of this will be on the third exam. This material will be tested for the final exam. But I wanted to get going on this today and to cover at least some ground today, because I wouldn't be surprised if most of you, or maybe perhaps all of you, will end up needing to use logistic regression for your final paper in this course. Let me introduce it and then explain why it's likely that you'll end up using this technique. Logistic regression is a model, a statistical technique that predicts categorical outcomes from categorical and continuous predictors. So it's conceptually it's quite similar to linear regression that we covered in an earlier chapter. So that's the good news, is that this will not be completely unfamiliar. You'll see that this model is similar, and it reminds one of linear regression. But it's a model that's appropriate when you have a dependent variable that is categorical, is nominal, as opposed to being continuously distributed. If it's continuously distributed, roughly normally distributed, then you can use linear regression. But as we see with survey data that we've been using a lot in this course from the General Social Survey, a lot of questions are not continuously, the answers are not continuously distributed. They're often nominal, categorical, even dichotomous, even binary. In its simplest form, a set of predictors is used to predict whether a person falls into category 1 or category 0 of the outcome variable. Say, for example, a typical question in the General Social Survey is whether you're in favor of something or you oppose something. You agree with something, you disagree. Yes or no. How would you answer this question? Yes or no? Well, those are binary dichotomous variables. We've kind of covered this ground before. Well, when you have that as an outcome, you can't use linear regression because linear regression assumes that you've got a normally distributed dependent variable. So instead, we use, if you have dichotomous dependent variables like yes or no, agree, disagree, that's called, you're going to use binary logistic regression. And typically we want to have those two categories scored as, one category scored as a 1 and the other category scored as a 0. That's really the proper way to do it. You'll see very often in data sets that one category, say for example, males will be scored as a 1 and females will be scored as a 2. But technically speaking, when you're using this technique, you should have your dependent variable categories as ones and zeros. So you would want to recode that dependent variable so that it's ones and zeros, and the common sense, the most practical way of deciding what's going to be a 1 and what's going to be a 0 is you want to score the category as a 1 if it's the category that you think is going to have a higher percentage of people in category 1 that's correlated with your predictor. So let me give an example of that. You think that poverty is going to predict being a criminal versus not being a criminal. You would want to score criminals, people that say had a record or conviction or arrest or something, score them as a 1, and someone who had never had an arrest or conviction, whatever your definition is, as a 0, because it's easier to interpret your results if the high scoring category, the one that's likely to be poor, you if they're ones, and if the group that's going to be low, the non-criminal group is likely to be wealthier, and so you want them to be zeros. Very often, since I'm a criminologist, most of the time I score males as 1 and females as 0 because males are usually the badly behaving of the two gender categories, statistically speaking. So that's just a side point that you'll want to, if you use logistic regression for your final paper, or when we get to the point, I'll make an assignment next week to have you do an exercise in logistic regression. You want to have that dependent variable scored in terms of ones and zeros. Now, here's a big point. Remember that with linear regression, the model we estimate looks like the following. And here I've put that equation out again, where the score for a person's dependent variable, that's going to equal the sum of these component parts of the equation. So your score for the dependent variable, say how many years of school you've completed, is going to be the result of the b sub 0, which is remember, it's the y-intercept. When all the x's equal 0, then we predict that your score will be at that y-intercept, wherever that is on the y-axis. And then you've got these components here, the slopes multiplied by x sub 1, one predictor, and x sub 2, a second predictor, multiplied by its coefficient, its slope. And then also the final component there, the error. You add all of those parts together, and that's going to be what your score is for the dependent variable, say number of years completed. So we've been through this before. So there's this algebraic form of linear regression. So if we go through these again quickly, y equals the value of the dependent variable for whatever person you're focusing on, person I. B sub 0 is the value of y for person I when all the predictors are equal to 0. That's the y-intercept. And the other b's are the slopes for the accompanying predictors. X sub 1 is the value for the first predictor for whatever person you're focusing on, person I, whatever person from your sample. And x sub 2 I is the value of the second predictor for person I. And the e is the error part. Remember, the error is the difference between what this equation is going to predict for you and your actual score with this example, I'm using how many years of school you've completed. So it might predict 16 years of school for you, and yet you've got 18 years. So the difference between 16 and 18, that's the error, the failure to predict accurately. We call that the error. So this is sort of a rehash, summarizing again what linear regression, how it works. One of the assumptions of the linear model is that the relationship between the predictors and the outcome is linear. When the outcome is categorical, this assumption is violated. See, so this is one problem you have with using a dichotomous variable, categorical variable. And there's nominal variables, categorical variables that are 3 or 4 or 5 or 6 or 7 categories. For the purposes of understanding logistic regression, let's keep it simple and just focus on binary dependent variables, because that's much simpler than when we have multiple, more than 2 categories. Anyway, so binary logistic regression, we'll focus on that. So if you've got a binary dependent variable, it's likely that the relationship between a predictor, say poverty, and your dependent variable, the chance that you're a criminal, the probability that you're a criminal, that sort of math, that tends to not be linear. It tends to work not in a stair-step fashion, where you go up a little bit in poverty, and so that causes you to go up that same kind of proportionate amount in your risk of being a criminal, your probability of being a criminal. The math usually doesn't work out that way. And so logistic regression adjusts for that fact that the relationship tends not to be linear. So that's a kind of a basic point to remember about logistic regression. It's a technique to help get around the fact that your your relationship is probably not going to be linear, and it has to be linear to conform to the assumptions, right, of linear regression. Okay, so one way around this problem is to transform the data using logarithmic transformation, which is a way of expressing a nonlinear relationship in a linear fashion, should say in a linear way there, linear fashion. So this logistic regression makes use of this logarithmic transformation, which is a technical thing. It's just changing the scale of the dependent variable so that it ends up getting around the problem. It ends up being like linear regression, but using this kind of alternative technique of sort of a transformation. Don't worry about the technical aspects of that too much, because again, I'm going to avoid in this chapter getting too heavy in terms of the technical math aspects of it. I'm interested more in sort of a common sense understanding of when to use this technique, how to interpret the findings, when not to use it, or problems that you run into when you use it, that kind of thing, more practical issues. Okay, so logistic regression uses this transformation, this logarithmic transformation, to express the linear model equation in logarithmic terms. And this is where this logit or logistic comes from. It comes from this logarithmic transformation that you're doing there. So really this model is very similar to linear regression, but you have this transformation, which gets around the assumption of linearity. It's a way around that problem. Okay, in logistic regression, instead of predicting the value of y, like we do in linear, from the values of the predictor variables, instead of predicting, how many years of school you completed, we predict the probability that person I, whoever we're focusing on, belongs to category 1 in the dependent variable instead of category 0. So the probability of y, of the y equals 1. So it's you're trying to predict, so let's say that we're trying to predict if I'm a criminal or not. And we can look at the overall probability in a population, and we say, well, convicted of some crime, 10% of the population has been convicted of some crime. So the baseline probability that you're a criminal, if we don't know anything more about you, we're going to assume that there's a 10% chance that you've been convicted of a crime. That's the background, the baseline probability. Well, when we put predictors into this model, and this is generally used as a multivariate model, just like with linear regression, where you have multiple predictors, not just one, but you have maybe one predictor that you're most interested in, and then you have several control variables just to make sure that you're including other factors that you think matter. Anyway, so what we look to see is, let's say that you're poor as opposed to being well off. Well, then that may increase. We can look and see how much that increases the probability that you've been convicted of a crime. And maybe if you're poor, it raises the probability from that baseline of 10% up to a probability of 20% that you've been convicted of a crime. So that's the kind of approach that this logistic regression model takes, is it tries to predict the chances that you fall into category 1. And so if we want to turn away from this criminological example to another one, agreeing with some attitude, it could be, that if you're more educated, then that predicts that you're strong support for for aggressive pro-environmental measures increases from a third to 2/3 or something like that, as the probability of that, just to give a different kind of example. So it's all about predicting probabilities as opposed to exactly what your score is. I finished 16 years of school, for example. It's what we're trying to predict is different. Probabilities instead of what your exact value is on the dependent variable. Because if you think about it for a second, whether you fall into category 1 or 0, it's all or nothing. You're either 1 or you're 0. You're a convicted criminal or you're not. And so it's not like a continuous variable where it goes from how many years of education you are, all the way down from less than high school up to graduate school, kind of a thing. There's gradations there, a continuum. So it makes sense to try to predict where you fall on that continuum with a linear regression model. But with logistic regression, it's which box you fall into. It's 100% one or the other. And so the way we make it more continuous, if you want to think of it that way, is what's the percent chance, the probability that you fall into category 1 instead of 0. So now this next point, instead of the estimated model being a straight line, it's the shape of a slanted S curve. So it's kind of in the middle of the curve. It's kind of a straight line, like a linear regression. But at the tails of it, down at the bottom and up at the top, maybe I could possibly show you a picture of what a logistic regression curve looks like. But it's pretty easy to imagine. So just imagine that slanted line like it was linear regression. But at the bottom of it, it curves out like an S. And at the top of that line, it curves down, flattens like an S. And so when you do that, it helps to predict more accurately your dependent variable. With a linear regression, it's going to be off, especially at those tails. Down at the bottom of the S and up at the top of the slanted curved S, you're going to be off at the edges. And so this helps to make your model more predictive, more accurate. So think of it, I use this term asymptotic here. See, such a curve assumes that a 0 and 100% probabilities are unlikely. So not too many people are going to be a 0% chance of being a criminal, or a 100% chance of being a criminal. Human beings are too complicated. They're not going to be 0% chance. You may have a great background with every privilege in the world, and there's a chance you're going to be a criminal. It's not going to be 0. And you can have all the deck, totally stacked against you, every social and psychological factor working against you, and you're still a law-abiding, well-behaved person who never gets in trouble with the law. Nobody has a 100% chance of predicted, chance of being a criminal, because people are just too complicated. It's not extremes like that. So logistic regression helps get around that problem, and you have this S-shaped curve where as that linear regression, that slanted line gets close to the axis, the x-axis, it becomes asymptotic, meaning it gets closer and closer and closer to touching the x-axis without ever actually touching it. So your chance never becomes 0. It just get closer and closer to it. And the same thing at the top end, that as you get close to 100% up at the top right-hand side of this slanted curve, that curve will get closer and closer to 100%, but it'll never reach it. So that's what they mean by asymptotic at the extremes, either 0% chance or 100% chance. So just imagine that S curve. It would be helpful if I got a visual for that. Maybe I can do that. As with linear regression, a slope is estimated from the data for each predictor, but instead of using the least squares method, which is ordinary least squares, I haven't stressed that term that much, but that's what we typically use when we're estimating linear regression, is this least squares method, where you're trying to minimize those errors. For each person, if that model predicts for me 16 years of school and I've done 18, well, that's 2 years of error there, or 2 years off. And the math tries to minimize that error for each person in the sample. So that's what they mean by least squares, is kind of a error minimization. So it's just, and again, it's math. We don't need to get into the technical aspects of that. For logistic regression, they typically use what's called maximum likelihood estimation, which is a little bit different in terms mathematically, but it's doing the same sort of thing for us. It's trying to come up with the best possible model to summarize and reflect the data from our sample. But this maximum likelihood estimation, it selects coefficients that give predictions of the Y category for person I that what category that they're going to fall into as closely to reality as possible. So again, you're trying to maximize the chance that you're predicting correctly whether is this person a criminal, are they not a criminal, and how often do you make an accurate prediction, how often do you make a mistake and make the wrong prediction. It's trying to minimize the error in that way. So it's a minimizing error is just done in a different way. Again, I want you to be familiar with these conceptually, but don't worry too much about the details, because again, my philosophy is to avoid the more technical aspects of the math. Okay, so your predicted Y will be a probability of falling into category 1. But of course, it's a probability, it's a prediction. So prediction is one thing that's helpful with this technique is to separate prediction from reality. Because the reality is you're either a convicted criminal or you're not. Your reality is not that I'm 80% chance of being a predicted, of being a criminal. The reality is I either am or I'm not. But we're trying to predict which box you fall into. And so it's helpful to kind of separate those two. That we're saying for the whole sample, if you're poor as opposed to being well off, that you go from a 10% chance of being a criminal to be a 20% chance of being a criminal. You double your chances of being a criminal. But we're saying that's based on the whole sample. But if you're talking about one individual, real life individual in that sample, they either are or they're not, right? So the prediction is kind of generated from the whole sample. It's not generated from one person because one person either is or isn't. But we're making an educated guess, sort of a prediction based on the sample characteristics. What's typical for the whole group of people, the whole sample. Anyway, I shouldn't make too much of that. It's not that big of a deal for us to worry about. Okay, when we assess how well the model fits the data for a linear model, we see how close the predicted Y values are to their observed counterparts. We do much the same thing in logistic regression using a statistic called the log likelihood. So again, technical, it's just the statistic, the proper statistic that we use that gives us a measure of how accurately we're predicting reality, right? How often we get it right, how often we get it wrong, which box you fall into. And so this log likelihood is a measure of how powerful, how strong, how accurate our model is in summarizing the data. If we, let me hold on to that and we'll continue on here. I'll talk about this a little bit more. So the log likelihood is based on summing the probabilities associated with the predicted Y and the actual Y outcome. So it's the difference between what we predict and what we actually see in people in our sample. It's an indicator of how far short the model comes from predicting correct outcomes 100% of the time. So it's an indicator of kind of the error in our model, the misprediction, the lack of accurate prediction in our model. So large values of log likelihood indicate a poorly fitting model. So another way of putting that is if you get a log likelihood statistic when you're doing logistic regression, that you want it to be low. Because a low number means you've got a good model, a model that predicts well your dependent variable. If you have a big, huge log likelihood, then that means you have a bad model. There's a lot of error. You're mispredicting quite often. So it's kind of, let me give you an example of how it's the opposite of like chi-square. When you get a big, huge chi-square number, that means that you've got a strong model, that you're predicting well, or that you're explaining a lot when you have a big chi-square number, although that's not very accurate because the big chi-square also comes from a big sample size, so it's rough that way. But still, with these statistics, sometimes small is good and sometimes big is good. So with log likelihood, small is good because that indicates a good fitting model when you have small log likelihood. Okay. Now, there's as usual, it's never simple in statistics. You'll have other statistics which measure the same kinds of things. The deviance statistic, this is closely related to the log likelihood. It is often referred to as -2LL because of how it's calculated. It's more convenient to use because it has a chi-square distribution, which makes it easy to decide statistical significance. So again, kind of a specific technical point there. But as you see, there's often statisticians will come up with different statistics, which may have advantage over other statistics. So deviance is an alternative to this log likelihood. One important use of both log likelihood and deviance is to see if one model is a significant improvement over another. So we use this log likelihood or deviance statistics, not only to tell us if we've got a good model, that are all of our predictors, everything, does it do a good job of predicting our outcome, our dependent variable or not, but it also is useful in you can look at the change in the log likelihood or the change in the deviance after you've added an extra predictor in your model, or maybe a couple of predictors. If it becomes significant, if the statistics become significantly improved, you could say, okay, adding in drug use significantly improved our model of trying to predict criminality. And so you can look at the deviance or log likelihood statistics and figure out if that adding another predictor significantly improves the power of your model. So that's one use that these have on top of just general, goodness of fit statistics, how good your model is. So we merely take the new model deviance and subtract it from the deviance from the baseline model, and the difference is called the likelihood ratio, which has a chi-square distribution with degrees of freedom equal to the number of parameters in the new model minus the number of parameters in the baseline model. So again, technical stuff. Degrees of freedom, these are numbers that go into calculating your likelihood ratio. Again, stuff that for the purposes of this course, I don't want to stress too much because I'm shooting here for big picture as opposed to, the nitty gritty. So, but again, you'll look at the output when we do a couple of examples of logistic regression, and you'll see the different statistics that are available and how you can use them. Anyway, but this is how you would go about finding out if adding an extra predictor made your model truly more powerful or not, if it didn't make a significant meaning real difference to the predictive power of your model. Okay, we've seen how the multiple correlation coefficient and R squared is the one that I focused on before when we were talking about linear regression, that is a very useful statistic to assess how well the model fits the data in linear models. So remember that, just to review, that the R squared is a number that goes from 0 to 1. It's like a proportion, like 0.5, 0.6, 0.7. And so if you got an R squared of 0.5, that means that all of your predictors together explain 50% of the variation in your dependent variable. So R squared is a very useful, very neat little statistic to tell you how powerful your model is, but that's only for linear regression. We can't use it for logistic regression because it's not appropriate, it's not correct. So we can see here on the next page that while the likelihood ratio statistic gives us a measure of goodness of fit, there's a measure available for logistic regression that is similar to R squared. It is called the R statistic. It's a partial correlation between the outcome variable and each of the predictors, and it varies from -1 to +1, and you should not square this number to get an R squared. So that's just an alternative. There's not just one way of doing it. But this is one way that you can come up with an alternative to give you something like an R squared statistic that will tell you how well your predictors do in predicting the outcome on the dependent variable. Now, I think this will be the last point I'll make here, because we're kind of running long in this video segment. We'll pick it up next time. But let me say that there are several, not just this R statistic, but there are several analogs, meaning similar statistics similar to R squared, which are appropriate for logistic regression, that help you tell you how strong of a model you have. And those, again, don't stress too much about these. I'm not going to really stress these for testing purposes, because there's a lot of different ones, and the point is to know that there's different options out there, and they all have their strengths and weaknesses, and different people go different ways. But you just need to understand that there are different ways of trying to assess the strength, the predictive strength of your whole model with all your predictors in there. So you've got Hosmer and Lemonshow's measure, Cox and Snell's measure, Nagle-Kirk's measure, and pseudo R-squared. Nagle-Kirk's and pseudo R-squared are the ones that I've seen most often in different statistical output. But they all do a similar sort of thing, which is come up with an alternative way to give you an R-squared-like number. Conceptually, these measures are somewhat the same, and they all indicate how strong your model is. So again, maybe we'll come back to this and look at this again when I do an example on our website of logistic regression. But let's stop it right there.